In our continuing story of the structure of the atom, we will discuss in this section the Bohr model and how it is related to the atomic spectra of various elements. A gas discharge tube is a device very similar to the cathode ray tube that was used by J.J. Thomson in his discovery of the electron. If the tube is filled with a gas, as shown here, for things like elemental hydrogen or deuterium or elemental nitrogen, oxygen, or even mercury, you end up getting, when the tube is turned on, various colors. These colors are very specific to the element that is present, and when you pass the light coming out of these tubes through a prism or a diffraction grating, you can observe what is referred to as the line spectrum for that element. Shown here are the line spectra for three elements. For the moment, I'd like to focus in on the spectrum of hydrogen. The scale is for the visible portion of the spectrum, which is roughly between 400 and 800 nanometers of wavelength. And it turns out that for hydrogen, you typically observe four emission lines: a red line, a teal or blue-green line, a blue line, and a violet line, in order of decreasing wavelength. The separations in terms of the changes appear to be very systematic, and so this prompted a number of researchers to try to come up with a mathematical model that describes what is happening for hydrogen. It turns out that for the other elements, the patterns are less easily understood, and for some elements there is quite a number of lines in not so easily understood patterns. It turns out that Balmer was able to come up with a mathematical formula that fairly accurately corresponded with the wavelengths for the emission for hydrogen. The equation is shown here. The equation states that the inverse of the wavelength in meters is equal to some constant, which is known as the Rydberg constant, which has a value of 1.097 times 10 to the 7th reciprocal meters, times the difference between the inverse squares of various integer values, where the integer values are whole numbers that could be numbers anywhere from 1 to higher possible values up to 5, or possibly even 6. Turns out that the n values were given subscripts. The f stands for the final situation, and the I stands for the initial situation. Balmer found that if he used the final integer value of 2 and the initial values where the n value is something higher than 2, 3, 4, 5, or 6, he was able to match the wavelength very closely to what was observed experimentally. Niels Bohr was able to come up with a model of the hydrogen atom that was able to explain both the spectrum and the formula developed by Bohr. He speculated that the hydrogen atom was similar to the solar system in that the nucleus of the atom was in the center of a series of electrons that were orbiting in circular orbits. And for hydrogen, there was only one electron, and in its lowest energy situation, the electron orbited at some distance without crashing into the nucleus. And it turns out that he assigned this as the n equals 1 level. It turns out that there were other possible orbits that were higher in energy. This, for example, the n equals 2 or n equals 3. And it turns out that the distance from the nucleus was increasing in each case, but the separation of the distance between the various orbits got smaller and smaller. Turns out then that the mathematical formula that would predict the energy of each of these possible orbits is given here. The energy is given the symbol of E, and we have on the other side of the equation a negative sign. It turns out that Bohr, by his convention, always stated that these energy levels were negative. And in the numerator of this equation, we have a series of constants. The R is the Rydberg constant, H is Planck's constant, and C is the speed of light. We have the value Z, which is the atomic number for the element of interest. Now, in this case, the Z was 1 for hydrogen, and the Z had to be squared, but 1 squared is 1. It is possible to use this equation for other elements as long as there's only 1 electron. There are very few examples where this equation will work. In the denominator of the equation is the what Bohr called the principal quantum number, the n value, which could take on values of integer values anywhere from 1 to infinity. The n had to be squared.